Hello again, students. Today we're going to do another sample problem that basically is going to just have us convert back and forth between the various different ways that chemists like to report concentration. So I've picked a couple things for us to do. First, I'm starting us with a 10% mass by mass solution of salt water, basically, sodium chloride and water. I'm giving us the density of that. We'll need this number for what I'm going to ask us to do. The first thing I want to know is what is the molarity of that solution. So certainly mass per mass is possibly just as common of a way to talk about concentration as molarity. So you should know how to go back and forth between them. In part B, I'm going to bring up molality. That is not very commonly used, but it is important for things like colligative properties. And it can be a little bit of a pain, quite frankly, to go back and forth between that one and some of these others. But we'll go ahead and do a sample of that. And then we're going to go back to mass percent from this molal solution that we have. So let's begin with making sure everyone understands what this 10% mass per mass means. We're going to get rid of the percent. I don't want to think about 10%. I want to think about that equivalent ratio. So we're going to immediately here start talking about this instead, that ratio, that unitless value. That unitless value is equal to mass per mass. It is mass of sodium chloride per mass, and this is something you just have to memorize. It's solution as opposed to solvent. Mass of the full and complete solution. And in fact, almost all of the different ways, like part per million, or molarity, most of the ways that we talk about concentration in chemistry, it is solution in the denominator. This is the oddball. That guy, I'll remind you now, is not kilograms of solution, it is kilograms of solvent. And we'll come back to that though. What I'm being asked to do in this first problem, in part A, is I have something given to me in mass per mass, or mass percent. And what I want to do is I want to go to moles of sodium chloride, and by definition, molarity wants to have liters of solution. Again, notice both of these are solution in the denominator. It's actually going to make things a little easier for us. So either you have one big unit conversion or you do the numerator unit conversion independent of the denominator unit conversion, doesn't matter. But notice that the way to go between mass of sodium chloride and moles of sodium chloride is simply just the molar mass, and so we will use that. If I look at this and I say, how do I get from the mass of a solution to the volume of a solution, specifically in liters, hopefully you recognize density as being our key there. Again, I gave us the actual density. Remember, concentration is independent of the volume of the stuff you actually have, or the mass of the solution itself, so we have not actually been given how much solution we should be starting with. All we know is this ratio. I might suggest that we just say, all right, let's start with 0.1 grams of sodium chloride, and then down here for the denominator, which I'll treat as a separate thing, I would have 0.1 per 1, so I would have 1 gram of solution. I'll do these conversion factors separately. I'm in gram per gram, that gives me unitless. You could alternatively, you could just start in kilogram per kilogram, it doesn't really matter. All right, coming back up here, let's use our molar mass. So 58.44 grams of sodium chloride for 1 mole of sodium chloride. That is going to give me 0.001711 moles of sodium chloride. So we'll set that number aside as the numerator, and we'll come down here and we'll just go through our density and a unit conversion to get over to liters. We are saying the density of this saltwater solution is 1.074 grams per 1 milliliter of the solution. It's great. Grams are canceling grams. I'm in milliliters. Now I need to say that there are exactly 1,000 milliliters per 1 liter. And that is going to give me 9.311 E minus 4 liters. So I take this numerator and I divide it by this guy, and I'm going to write that number, nestle it in right next to the actual question, 1.838 molar NaCl solution. Okay, that's part A. Let's reclaim board space. Okay, part B, I say how much of each solution, those two solutions being the one that has salt and the other is just pure water, which we're just going to go with a nice, keep it simple density there. But how much of each of these would you have to mix together if by the end of that mixing I wanted to have 0.5 kilograms of water? That's my denominator. I didn't say of the full solution, I'm saying of just the water. And then I just put this little note as a reminder. Remember, you would have a combined mass. The solution would be heavier than that because it has some salt in it plus half a kilogram of water. So it would be greater than 0.5. We will keep it simpler and just say how much of that water. So here's where we start with this. If I have this information, 1 mol, that means moles of sodium chloride per 1 kilogram of my solvent, which is just the pure H2O here. So again, that's the oddball. It's not of the solution, it's of the solvent. I only want half a kilogram of water. So I need to cut this in half. So I need 0.5 mole of NaCl. That number would still have 3 sig figs though. And 0.5, this number, this guy would be an infinite sig fig, so we're just going to round it at the end though. H2O. So what I'm going to do is I'm going to use the molar mass here to get at the number of grams. Well, there was my molar mass from before, so I just need half of that number. So 58.44 divided by 2 is 29.22 grams of NaCl. How do I get a hold of that many grams? Well, that's where I can go in and I can use that mass per mass idea. So 29.22 grams of the solute. And how many grams of solution do I need? That's pretty simple math there. I'm going to write it clear over here though. I just have to move the decimal place. I need 292.2 grams of the solution. Because this is where the bookkeeping part gets important. We need to know that if I have that much solution, that is in part, and I'm moving the decimal place back again to this guy, to this number, 29.22 grams sodium chloride, but that is also the 292.2 grams of the solution minus whatever mass was sodium chloride. Notice there is a decimal place difference on those two numbers. And what that gets me is 262.98 grams of water. And notice that if you take the amount of water plus the amount of salt, you will get the 292.2 grams of solution that are in the middle. So what I've had to do is I've had to characterize this initial starting material so that I actually know how much mass is water, how much mass is actually my salt. That's going to really help me here with the molality idea. Because if you come back and remember what I asked for, I want half a kilogram of water. Well, here's how much I'm going to originally put in because of the mass percent solution. And it's going to bring with it all of the sodium chloride that I need in order to get that 1 molal solution. So look at this bottom number and just recognize that I still need 500 grams minus this quantity, 262.98 grams, which is 237.02 grams of pure H2O. That's what's going to get me ultimately that half a kilogram of water. So here's my answer for part B. If you follow, I need this. This is what's going to bring all the salt to it. So I need 292.2 grams of my 10% mass by mass solution plus this guy, 237.02 grams of pure H2O. Notice that if you add those two numbers together, it will indeed be greater than 0.5 kilograms. Looking ahead, because I'm going to want to know what is the mass percent, this is now doing work for part C, I'm going to need to know what the total mass is of this solution. So if I add that together, I get 529.22. That's grams. So now there's actually very little work that still needs to be done here for part C. And this is just me recognizing how a mass percent works. I erased the number before, but you'll recall that I have 29.22 grams of sodium chloride in my solution. That all came from this guy, because the pure water isn't bringing anything to the table. But that is 529.22 total grams of my final mixture. And when I do that out, I get 0.05521, or this is going to be my final answer, 5.52%. And I would put over there M per M, just so it's clear to everyone. Great, so I answered all my questions. Here was my answer from part A. This is my answer from part B, this information about how much of each. And here's my answer for part C. Hopefully everything made sense to you, and if it did, you should let your computer know.